Let's work through an example where we construct a confidence interval estimate of a proportion. A study was conducted in which 1,000 randomly selected Americans were asked if they believed the minimum wage should be raised. A total of 600 Americans said yes. Okay, before we continue, let's make sure that our requirements are met. Recall that the first requirement was that it was a simple random sample. Simple random sample. Okay. Is it a simple random sample? Well, the information they give us is that they were randomly selected, so we'll just make the assumption that it was a simple random sample that they took. The next is that the conditions of the binomial are satisfied. Recall those conditions. Number one, a fixed number of trials. Well, their N was 1,000, so they asked a fixed number of people. There are independent trials, and recall that's, if we think back, that means with replacement. Now, we would assume that they wouldn't ask the same person twice, but when we're talking about taking 1,000 out of all the possible Americans they could have pulled their 1,000 from, recall that we can assume independence if our sample size is less than or equal to 5% of the population size. We don't have the population size, but we certainly know that it's a significant number. Do we have two categories? Yes. The categories were, yes, they do believe the minimum wage should be raised, and the other would be that they didn't respond yes. Okay? Yes, or they didn't say yes. Is the probability of success constant? Well, we would just have to assume that probability of success, the number of people who are going to say yes, is a fixed number in the population. Now, that might change with time. People change their mind over time about things, but in that one moment, we would believe that the proportion of people who do believe this is a fixed probability. So those are the conditions of the binomial. Then the final requirement of a confidence interval estimate of the proportion is that we have at least 5 successes and at least 5 failures. Well, if we're looking for yeses, we have 600 successes and therefore 400 failures. So certainly we have 5 of each. So the simple random sample, the conditions of the binomial, we check that, and the last 5 successes, 5 failures. At least. So I'm just kind of abbreviating, but these are the things we just checked for. Okay, so let's move on. What we're asked to do is to construct a 90% confidence interval estimate for the proportion of Americans who believe that the minimum wage should be raised. So what information do we have? Well, we know that our sample size was 1,000, and the number of successes was 600. That's our X. Okay, from this information we can compute our sample proportion, P hat. Recall that that is just X over N, or 600 over 1,000, which is 0.6. Okay. Now we can get Q hat. Once we have P hat, they are complements, so Q hat is equal to 1 minus P hat. Which is equal to 1 minus 0.6 or 0.4. Our confidence level is 90%. So that means, let's move this up a little bit. Okay, our confidence level is 90%. So that means alpha is 0.1 or 0.10 or 10%. So our Z, alpha over 2, critical value, is equal to Z of 0.05, 0.10 over 2, which is 1.645. Okay. So now we have everything recorded that we know, and let's look at our margin of error. We want to calculate E, which is Z alpha over 2 times the square root P hat times Q hat in the numerator over N. So 1.645. P hat we said was 0.60. Q hat 0.40 or 0.4 over N, which was 1,000, and all of this goes under the square root. And that comes out to be 0.025484. Okay, so we want to construct our confidence interval, and recall that's P hat minus E less than P less than P hat plus E. We have all the information we need now to do that. 0.6 minus 0.025484 less than P hat plus, oh sorry, P hat is our 0.6, right? Plus 0.025484. Alright, so the subtraction here gives us 0.57452. And here when we add, we get 0.62548. And finally, we said we'd round to 3 decimal places for the proportion, so we get 0.575 for our lower confidence limit and 0.625 for our upper confidence limit. So this is the 90% confidence interval estimate for the proportion, the true proportion of Americans who believe that the minimum wage should be raised. Recall we only had one sample, and so we realized there's going to be variability. If we pulled another sample of 1,000 people, we might not get 600, we might get some other number, right? But so we would like to be able to estimate better than what one sample can do. And so what we do is use our one sample to make this estimate. And we determined we wanted a 90% confidence. Well, let's see what happens if we change that confidence level to 95%. Okay, so everything's the same except for our confidence level, and that changes our alpha, right? So for a confidence level of 95%, we now have an alpha of 0.05 or 5%. So our Z alpha over 2 is Z 0.025, half of 5%, which is 1.96. Okay, so back to a calculation of the margin of error. I won't write the formula again, but it's the Z alpha over 2, and then I need P hat, which hasn't changed, 0.4. Oh, sorry, that's my Q hat, isn't it? It doesn't matter the order here that we multiply. Q hat and P hat go in the numerator over N, and this is all under the square root. Okay, and this time we get 0.030364. So remember, we take P hat 0.6 minus 0.030364, 0.030364, and P hat plus 0.030364. Notice I'm carrying this out because I'm going to have to round eventually, but I don't want to do the rounding to 3 too soon, or I'll introduce rounding error in my answer. Okay, here we get 0.56964. And 0.63036. Now we round to 3. And here we'll get 0.570, and here 0.630. So that's our new confidence interval estimate, changing the confidence level to 95%. Let's do one more for the third commonly used confidence level, which is 99%. Everything else stays the same. New confidence level, 99%. Now alpha is 1% or 0.01. So z alpha over 2 is z 0.005, half of 1%. And this z value is 2.575. Okay, so E is equal to 2.575 times, and then we have P hat, Q hat, over N, take the square root, 0.03989. Okay, so 0.6 minus 0.03989. This is the lower limit, and 0.6 plus 0.03989. And here we get 0.56011 and 0.63989. Final, the rounding to 3, 0.560 and 0.640. Okay, so what I want to note, the reason I did all three is I want you to notice one important thing about these different confidence levels. I've left everything else the same. That's the only thing we changed. So let's investigate this, our results on a number line. Okay, put a few values here. Here's my 0.6 and 0.625 and 0.630. I'm just going to put some increments here, and let's see, about right here, 0.640. Okay, and let's see, 0.575, and maybe right in here would be 569 and 0.560. Let's see, did we get those right? I think there was one maybe different. 570. This one should be 570. Here, let me just fix that. This is 0.570. They're not exact, but it gives you the idea. Okay, our 90% confidence interval estimate. The first one we calculated. Let's run back. 0.575, 0.625. So right here, from 0.575 to 0.625. This was our let me leave it this, 90%. Okay, then we calculated the 95% confidence interval estimate, 0.570 to 0.630. 0.570 to 0.630. This was our 95%. And then the last one we did was from 0.560 to 0.640. And of course they all centered on our P hat. But what I wanted to point out to you is, as we want a higher level of confidence, our interval gets wider. Now why would that be? Well, just think about if you were throwing darts at a board. You would be more confident that you would hit the bullseye if the bullseye was bigger, right? If you didn't need to be so confident about it, you could have a smaller bullseye. So if you think about it that way, maybe it makes a little more sense. But this is important and to note about confidence intervals. The higher the confidence, the wider the interval.